Hi everyone, welcome back. In this particular video, we're going to talk about alpha-alkylation using the enolate. Now, as we know, enolates are nucleophiles, and the nucleophiles can be used for alkylating the alpha position. So they can be used for achieving an alpha-alkylation. So that would mean adding an alkyl group to the alpha carbon of a compound that has an active alpha hydrogen, where it can deprotonate or where an enolate can be formed. So an example is here, which is a very generalized scheme here. So if we have a compound where we have an alpha carbon, and recognize that what's important is to have an alpha hydrogen, because only then you would be able to form an enolate. And this compound here has 3 alpha hydrogens. We can draw out one of them. So when you treat this compound with a base, that would give you the enolate. Okay. So when this compound is treated with the base, you're going to make the enolate. So the base can go ahead and deprotonate the alpha hydrogen, and that will give us the enolate corresponding to this molecule or this compound. Okay, so we get the enolate that way. And then in the second step, if you react this enolate, so this is the first step with base, and the base, it may have a negative charge on it, so the base can go ahead and deprotonate, and that's how we make enolate here. And in the second step, we react this enolate with an alkyl halide. Okay, so in an SN2 manner, or using an SN2 reaction, what the enolate can do is it can go and do an attack on the alkyl group, on the alpha carbon of that group. We'll look at some specific examples. And the halogen would leave, and that would give us an alkyl group connected to that alpha carbon. Now, in principle, this compound here, or the product here, has 2 additional alpha hydrogens. That means we can repeat this process again. We can do it over and over again, like until we've exhausted all the alpha hydrogens that are present. But when we try to do this reaction, the role of the base is very important here, and we will discuss that. To understand the role of the base in this particular alpha-alkylation reaction, or in an alpha-alkylation reaction, we're going to consider 2 bases here. One is sodium methoxide. Now, this is going to be representative of any alkoxide base. So if we had any sodium OR base, that would be represented by the sodium methoxide, or even sodium hydroxide or potassium hydroxide, like a hydroxide base, that would be representative. The other one is lithium diisopropylamide, which is a relatively much stronger base, or maybe sodium hydride, like another base that we have seen for these deprotonation reactions. So now when we use sodium methoxide as a base for generating the enolate, the base here is going to deprotonate the alpha hydrogen. The electrons would come here, and the double bond opens up, which gives us the enolate. And again, realize that the enolate is the nucleophile that we're trying to synthesize here. And plus, it's going to make methanol, which is the conjugate acid of the base that we're using. And as we know, based on pKa values, this reaction is not favorable. Okay, this deprotonation does not work effectively. So at equilibrium, you've generated a little bit of the enolate, which is a nucleophile that you want. Okay, so that's one of the nucleophiles in the system here. But because this reaction is not favorable, we have actually a lot of another nucleophile, which is sodium methoxide. So this is a second nucleophile that's present in the system. So when you do this deprotonation using, let's say, sodium methoxide or sodium hydroxide, you will generate two nucleophiles, or you will end up with two nucleophiles in your system. One is going to be the base itself, the base that you used, and the second is going to be the enolate that you generated. Okay. And so essentially what happens is when we do the second step, which is adding the alkyl halide in. So if you bring in the alkyl halide in the second step, there are two potential nucleophiles in the system. One is the enolate. So the enolate can go and attack the alkyl halide and give us the SN2 reaction. So that will give us a product that we want, okay, which is the alpha alkylated product. It will give us that product, which is the alpha alkylated product. But the second nucleophile is the methoxide, or the initial base that we used. And so this base can also go and attack the alkyl halide, and the halogen can be kicked out. And that would give us a second product here, which is going to be ROCH3. So we would end up with a mixture of two products. The SN2 reaction can happen using the enolate as the nucleophile, or it can happen using the alkoxide as the nucleophile. So we get a mixture of products here. Two products are formed here. Okay, so when the methoxide attacks the alkyl halide, you will get an ether as your product. Or if it's a hydroxide, you will get an alcohol as your product. Now, this situation can be avoided by using a stronger base like LDA or sodium hydride, because when you react the carbonyl compound or the alpha carbon compound with LDA as the base deprotonates the alpha hydrogen, and that's going to generate the enolate. Now, based on pKa values, this reaction is actually favored in the forward direction. That means we make a lot of the enolate, which is our nucleophile. In fact, this reaction would quantitatively convert the alpha carbon compound into the enolate, which means we only have one nucleophile in our system because the base itself has been used up in converting the alpha carbon compound into the enolate. And so that means when we add the alkyl halide in the second step, the enolate is the only nucleophile which can attack the alkyl halide, and it would give us the alpha alkylated product as the only product here. That would be the only product compared to the use of a methoxide or an alkoxide or a hydroxide base, where you would get a mixture of two alkylation products. Now, the same sort of the same outcome here can be achieved by using sodium hydride, because sodium hydride is also a strong enough base to push this equilibrium to completion, where we get the enolate quantitatively. Okay, so that's why the choice of the base or the role of the base is very important when it comes to the alpha alkylation reaction. Next, we're going to talk about the generation of thermodynamic and kinetic enolates, or the formation of thermodynamic and kinetic enolates. What are these? And so for the purpose of this discussion, I'm using an unsymmetrical ketone here. Okay. Now, this ketone is unsymmetrical, and because of that, what we have is we have two possible alpha hydrogens here, and they can both be deprotonated. And I've sort of identified some salient features of these alpha hydrogens. Notice that H alpha 1 is connected to is based on a primary carbon. H alpha 2, on the other hand, is based on a secondary carbon. But irrespective, when this carbonyl compound is reacted with a base, the base can deprotonate H alpha 1, and which means the electrons here would go up and the double bond would open up, and this would give us an enolate where there is a double bond on the right hand side. Okay, so between the carbonyl carbon and the primary carbon, we have a negative charge on that oxygen. The base could also deprotonate H alpha 2, and if that happens, then the electron pair moves up and the double bond would get pushed up similarly. But this would give us a different enolate where the double bond is between, or the alkene double bond is formed between the secondary carbon and the carbonyl carbon. Now, between these two enolates that can potentially form, let's think about which one would be formed faster. Okay, which one would be formed faster? Now, if you think about what's going on here, the base has to deprotonate H alpha 1, which is connected to a primary carbon, or it has to deprotonate H alpha 2, which is connected to a secondary carbon. Because H alpha 2 is connected to a secondary carbon, okay, it's the deprotonation, the removal of that is going to be a slower process because there's more sterics involved there. Whereas for H alpha 1, it should be a faster process. So the first enolate here, where the enolate, the double bond is between the carbonyl carbon here and the primary carbon, this will be formed faster. This will be formed faster. And so because of that, this enolate is called the kinetic enolate. Okay, so that's the enolate that's formed faster between the two enolates. So now let's ask the other question. Which of those two enolates, or which of these two enolates, is the more stable enolate? And the answer would be the second enolate here, because now the double bond is more substituted. And in fact, I would like to point out that here the R group should be written down here, because that would give us the E enolate. Okay, that would give us an E configuration to that enolate. The structure that I had written previously was a Z enolate. So this would be the enolate that's formed. And this is the more stable enolate between the two. Okay, and for that reason, this enolate is called the thermodynamic enolate. Okay, so between the two enolates, one is the kinetic enolate because it is formed faster. The alpha hydrogen can be deprotonated much easily, much readily. The other one is the thermodynamic enolate because overall it is more stable between the two. Okay, so this is formed faster, but this is less stable. This is more stable, but it is formed slowly compared to the other one. So that's how we get the kinetic and the thermodynamic enolates. Now, we can put this on a reaction profile diagram. And essentially, we have the two alpha hydrogens, H alpha 1 and H alpha 2. The deprotonation of these two would give us the thermodynamic and the kinetic enolates. The thermodynamic enolate is going to be the more stable enolate. So overall, this would be lower in energy compared to the other one. Okay, so that's our thermodynamic enolate. That's the thermodynamic enolate. And then the other possibility is that we make the kinetic enolate. This is formed faster. So if we plot a reaction profile diagram, and if this is the energy of the starting compound, this is the energy of that, and this is the energy of the, so that's the energy of, so this is on an energy scale. And we're plotting reaction progress, let's say. If you plot that, then to go from the alpha carbon compound or from this unsymmetrical compound to the kinetic enolate, it's going to be really fast, okay? It won't need a lot of energy. But to go from the alpha carbon compound to the thermodynamic enolate, it's going to need more energy, okay? Because we are trying to deprotonate a more sterically hindered alpha hydrogen here. So that's why the energy, or it would be harder to do. And that's sort of reflected in the higher activation energy that we need, because recollect that this difference is our EA, activation energy. This difference here is our EA, activation energy. So the activation energy needed to form the thermodynamic enolate is much higher. So it is formed slowly, but it is more stable. The activation energy needed to form the kinetic enolate is lower, and so it is formed much faster, but it is less stable. Okay, so those are the kinetic and the thermodynamic enolates. Now let's see how we can change or control the reaction conditions to favor the formation of the thermodynamic or the kinetic enolate, one versus the other. So if we consider this alpha carbonyl compound, and if we react it with a strong base like LDA, but at a low temperature, okay, really low temperature, let's say negative 78 degrees Celsius. We do it at really low temperatures here. What's going to happen here is LDA being a bulky base. So recollect, LDA is this nitrogen-based base, which has two isopropyl groups on it. So at the low temperatures, LDA being a bulky base, it would prefer to deprotonate the less substituted alpha hydrogen, H alpha 1 over H alpha 2. And so the enolate that we will make here is going to be the kinetic enolate. This will give us the kinetic enolate. Okay, so we can synthesize or we can generate the kinetic enolate by doing the reaction at low temperatures using a bulky base. Okay, but if we do the same reaction at relatively higher temperatures, so here's H alpha 1 and here's H alpha 2, if we do the reaction at relatively higher temperatures and we use sodium hydride as a base, and let's say we do it at room temperature, so 25 degrees Celsius, relatively much higher compared to the other conditions. So it's about almost 100 degrees higher here, okay? It's negative 78 versus 25 degrees Celsius. So we're almost 100 degrees hotter here. So when you do this, then the sodium hydride under these conditions would give us the thermodynamic enolate. And again, the R group would be pointing down. It would give us the thermodynamic enolate. And at room temperature, under these conditions, what's going to happen is the sodium hydride would still have the propensity to deprotonate the less substituted alpha hydrogen, and it would give you the kinetic enolate initially, but it's going to equilibrate. And when the equilibrium is achieved, it will convert to the more stable enolate, which is the thermodynamic enolate. So there's going to be some equilibration that happens, and at equilibrium, you will have the more stable enolate that's formed. And then once you do these reactions, you can use the kinetic or the thermodynamic enolate for doing further reactions. You can react it with an alkyl halide to achieve alpha-alkylation. Because if I react this with an alkyl halide now, let's say R prime X, then the enolate is going to attack that R group, X would get kicked out. And so our product, we will achieve alpha-alkylation at the less substituted alpha carbon. Whereas in this particular case, if we do the same reaction, we will achieve alpha-alkylation at the more substituted carbon. So our product is going to be this ketone. So we've put the alkyl group on the less substituted, or we can choose to put the alkyl group on the more substituted carbon. So that was the discussion on kinetic versus thermodynamic enolate, what these are, how they differ, and how can we control the generation of the kinetic versus the thermodynamic enolate. I hope you find the discussion useful.